Now, if I flip this molecule, I'm going to get the enantiomer. So this is lactic acid. So these are ways of representing enantiomer. So let's welcome back to Academy X tutorials. Today we are going to be looking at enantiomers, stereomers, and race mates. So let us go back to when we were talking about optical activity. We said that optical activity is the ability of a compound to rotate plane polarized light. So the ability to rotate it to the left or to the right is optical activity of a compound. So optical isomers, remember we have geometric isomers, we have optical isomers under configurational isomers. Now what are configurational isomers? Configurational isomers are isomers in which there is a fixed rotation, like rotation is fixed, it is not movable. We have the geometric and we have the optical. Now under optical isomers, we have the enantiomers and the diastereomers. So we are going to talk about this optical isomerism proper. So in optical isomerism, a compound which shows optical activity is not superimposable with its mirror image. So what it means is that if you get an mirror image of a compound, it cannot be superimposed. Example, these are my two hands. Let me give you an example. This is my hand, this is my left hand, this is my right. Now, this is a mirror image of each other. So what it means that this mirror image, if I put them together like this, I cannot superimpose them. Superimposition means something that looks like this. I don't know if you can look at what I'm saying, but these are my hands. If I put them like this, they cannot be superimposed. So it means that my hand is a chiral object. So the same thing happens in molecules. So in molecules, when I have the mirror image and it cannot be superimposed on each other and it cannot align when I get the mirror image, I said that it's an optical compound, an optical isomer. Now, let us look at the properties of these optical isomers. Now, we said that most times optical isomers do not have the same biological action. They have the same physical property, they have the same chemical property. Like example, something like S-lactic acid and R-lactic acid. They have the same chemical properties. They may be white in color, they may give reactions with and some reagents. They can do many reactions, they have the same boiling point, melting point, density, name them. But then when they are placed in a chiral environment, example of chiral environment is your human body. The human body is a chiral environment. Now, when they are placed in a chiral or disymmetric environment, I can also say that our body is disymmetric. They tend to possess what we call chirality. So a part of your body may be chiral and may attract the same type of molecule that has the same chirality with it. So when we look at the human body and when these substances are in the human body, they may have different biological and toxicological action. Example, something like ethambutol, ethambutol causes blindness, causes optical neuritis, while the R form is okay for treating tuberculosis. So it is because of this optical isomerism. So one isomer is dangerous and one of them is useful in treating tuberculosis. But if you look at the two enantiomers, they are the same thing, the same color, texture, density, chemical properties, etc. etc. Now, we said that these optical isomers can also occur as meso compounds and race mates or race mate mixtures. So I'm going to look at them one by one. So let us look at the first one. The first one is enantiomers. Enantiomers. Now, what is an enantiomer? An enantiomers are mirror images of each other. Now, they rotate plane polarized light by equal amounts, but in opposite direction. Example, this particular thing can rotate, the S1 can maybe rotate plane polarized light by plus 25. Then this arrow form, we also rotate plane polarized in the negative direction by the same 25. So they rotate plane polarized light in different direction, but in the same magnitude. Now, they have the same physical and chemical properties except in a disymmetric environment, for example, the human body. That is why most of these enantiomers have different biological and toxicological actions. So let us look at lactic acid. Now, lactic acid, this is S-lactic acid, R-lactic acid. They are enantiometric representation. We're going to talk about that in subsequent classes. We talk about the presentation of the enantiomers. Now, this is an enantiomer of this. Now, if you can remember in this last classes we did, you can say that these particular centers are chiral centers. Remember what you said about point chirality. You said that in point chirality, each center has 4 different atoms. For example, this is carbon 1, 2, 3, 4. They are all different. So this is a chiral center. So when I draw the enantiomer, this is how the enantiomer looks like. So when you flip this image by 180 degrees, you form the enantiomer. So this is the enantiomer of this molecule. Now, this enantiomer has the same physical and chemical properties, but they may possess different pharmacological or biological or toxicological actions. Now, these optical isomers have the same name. They bear the same name. One common thing about enantiomers is that they have the same name. But then you have to differentiate between the two enantiomers by using 3 methods. Number one, by their optical activity. I can decide to like put something like morphine. We have a negative and the positive. Say that the negative one is much more effective than the positive one. The negative one is the one that has pharmacological action, while the positive type of morphine does not have pharmacological action. So what it means is that the negative will rotate plane polarized light to the left and we call it levo rotatory. But then the one with plus rotates plane polarized light to the right, so we call it dextro rotatory. Now, this is one way of identifying optical isomers by stating whether they rotate to the left or rotate to the right. Now, this particular convention is gotten from experiments using optical apparatus, nickel prism, and the rest. Yes, an optical tube. So you are able to know the optical activity or the rotation of light by experimental methods. It's not something you can look at the molecule and know. Like I can't look at this molecule and know that it's minus, and I can't look at this molecule and know that it's plus. I will have to set up the apparatus, put the sample, and then check the angle of rotation. Now, the second one is relative configuration. Relative configuration is based on a compound called glyceraldehyde. We are going to see that in subsequent classes. So we have the D and the L, big D, big L. Big D, big L. This one can be presented by small d, small L. So take note of that. But when we see big D and big L, we are talking about relative configuration. Now, why is it relative configuration? Because we are trying to relate it to a simple molecule, a very simple chiral molecule. So it is relating to it. That is why we call it relative configuration. So we have D glucose, D mannose, L arginine, L-lysine, and so on and so forth. Remember I said that these enantiomers, whether they are labeled plus or minus or labeled D or L or labeled R and S, these optical isomers have different action. Example now, in the human body, the type of glucose we utilize in our body is D glucose. L glucose does not have any action. D glucose is a dextrose. And remember what you use dextrose to do. So it has an action in the human body. The L-dextrose is called levose. It doesn't have any action in the body. So D-glucose is the one that has the action because it is inside the chiral environment, which is the human body. Now, same for amino acid. L-amino acids are much more common and much more useful to man than the D-amino acids. So that is how it was created by God. So let's look at the absolute configuration. Absolute configuration is now centered on each chiral center. So the number of absolute configuration will depend on how many chiral center I have. For example, this has one chiral center, so I can represent it as S-lactic acid. If it has two chiral center, I can represent it as maybe 1S, 2S lactic acid. If it is 3 chiral center, I may say 1 arrow, 3S, 5 arrow, the absolute configuration. So absolute configuration deals with each stereo center. What is the optical nature of each stereo center? And it is gotten by CIP rules. We are going to look at CIP rules in subsequent classes. Now, CIP means can in gold rules. Can a gold. Now they are specific for each chiral center. So each chiral center has its own CIP. Now, if arrow is the configuration of a particular center, S will be the configuration of the enantiomer at that center. So if this center has arrow configuration, if I want to do the enantiomer, it will have the S configuration. That is what this point is trying to tell us. Now, let us do some few exercises here. Okay, now let us look at the ways of representation of enantiomers. So we said that enantiomers can be presented by number one, changing the hash and wedge bond. Remember what I said about the hash and wedge bond? This is the wedge bond, this is the hash bond. Wedge bond means that it is going backward, it's going forward, sorry, while hash bond means it is going backward. So if I want to draw the enantiomer, I'm going to put a mirror there. Okay, this is the aromatic acid. Let's look at the second one, which is changing substituent at the bond. So you can actually change anything here with this. Like you can change this to this to this with this with this, anywhere you want to change. Example, let's put a mirror. Put a mirror. We have COOH. We have C. We have, let's say, let's change this to CH3, and then let's change this to H, and then let's put our OH. This is lactic acid. Okay. Now you can also change another thing to give you the enantiomer. So maybe let's put COH here. Then let's put this C here. Then let's put OH here. Let's put CH3 here. And then let's put the H. Yeah, you can do it anyhow you want. It will still give you the enantiomer. So this is still lactic acid. So just by interchanging two places here, will give you the enantiomer. Now the last one is flipping the molecule 180 degrees. So if you flip the molecule, you get the enantiomer. Example, if I flip this molecule like this, C H. Now I've just succeeded in flipping this molecule by 180 degrees. Now if I flip this molecule, I'm going to get the enantiomer. So this is lactic acid. So these are ways of representing enantiomer. So let us do a brief summary of what we said about the enantiomers. We said that enantiomers are special optical isomers in which their mirror images are not superimposable on them. So you cannot superimpose the mirror images on the molecule. you cannot superimpose the mirror images on the molecule. Now, you said that these enantiomers have similar physical and chemical properties but different biological and toxicological action. Why is this so? Because this biological and toxicological action occurs in a disymmetric or chiral environment, example, a living organism or a human being. So physically and chemically they may look the same, they might even have the same name, but then in the body they have different action. Like what I said about a drug called etambutol. You said that etambutol is used to treat tuberculosis, but there's an enantioma it has that causes blindness. So we said that these enantiomas can rotate plane polarized light to the positive or to the right direction or to the left direction, which is negative direction. And they rotate this plane polarized light by equal amount but different directions. Now, these are ways of representing enantiomas. So we gave the different ways of representing enantiomas. So the enantiomas can be represented by plus and minus, which is the optical activity, or it can be presented by D and L, which is relative configuration based on a compound called glyceraldehyde. And then we have the absolute configuration, which depends on each stereo center, and we have the R and the S, RESI, that is the short form. Now, we said that enantiomas can be represented or can be gotten by number one, changing the hash and wedge bond, like we have here. So that S-lactic acid, when we interchange the hash and wedge bond, we get the R-lactic acid. Now, we also said changing substituents of the bond. So these are the bonds. If I change any substituent, keeping the bonds constant, I also get an enantioma. Now, the last one is flipping the molecule by 180 degrees. So if I flip this molecule by 180 degrees, it is going to form the enantioma. So that is all about enantioma. So in the next class, we'll talk about diastereomers.